Thank you. I would like to start by thanking Helen for inviting me to present here today. I'll try to be brief because I think we all need some refreshments. What I'll present here today is kind of like the more applied side of my PhD study, and how I use some of the techniques that have been presented here today to develop or at least come up with ideas on how to develop exploration techniques for Archean syn-volcanic deposits by applying cutting-edge isotope geochemistry. So I'm going to go through a short introduction, and then I'll jump into two case studies. So our motivation is quite straightforward. If you have a look at the map on the left, you'll see that there aren't many occurrences of VHMS systems in Western Australia, and those are represented by the yellow star. And especially, that's like very visual if you compare it to similar terrains like the Superior Province in Canada. And you can see that there are a bunch of VMS deposits over there. So our main motivation is, can we come up with ways to develop exploration tools which are maybe better equipped to finding these deposits, and are we able to detail better known occurrences? And I had a look at the Nimbus deposit, and it is actually a very interesting deposit because unlike your classic VHMS deposit, which has exhalation of metals onto seawater and that precipitates on the seafloor, the process of ore formation at Nimbus is actually replacement of the host rock. That means that constraining the relative of time is quite challenging. The timing of ore is quite challenging because you don't have, a clear stratigraphic marker. And in order to try and achieve that, what we use is a multidisciplinary approach that aims to constrain the different processes. So that's basically what this little infogram here illustrates, and that's the bulk composition of what my PhD study was. It's that I've used different isotopic techniques to constrain magmatism, the ore formation, the alteration, as well as account for processes that might have affected the deposit at a future time. And my goal was to build a 4D framework for the VHMS system, and that will lead us to understand the timing of ore formation, the source of metals and conditions for ore precipitation, and then lead to the discovery of new deposits. For the case of the Nimbus deposit specifically, throughout my study I've identified that there were two main significant events, one at 2.7 billion years, which is the volcanism, and then a younger alteration event at 2640, around 2640 million years. So basically you have two competing models, one of the syn-volcanic ore, and then another one that means that this ore is actually being formed at in a future time. And what I did to answer that is that I had a look at the different sulfide phases. So this is a description of all the sulfide phases from Nimbus, from a paper by Caruso and others in 2018. And in addition to these phases, we've actually identified an 8th sulfide phase, which are some sulfides, including galinas, which are related to late quartz carbonate veins that are seen to post foliation. So we basically measure the chemical composition of ore galinas from that polymetallic ore phase and the late galinas. And based on the difference in chemistry, we were able to constrain that the ore was actually related to the 2.7 volcanism and not to the later activity. So that in itself already represents kind of like an indirect exploration tool, because you now are much more confident in what is the process driving mineralization, so you can search for similar processes throughout your terrain. And if you want to get into the more specifics and the detail of the techniques that I've used and a lot of the capabilities of the John DeLater Center, this paper, it was recently published, and it's available free of charge for the next month. So if you want to read it, you can come find me afterwards, or you can contact me on social media, and I'll be happy to provide you the link. So, okay, now getting into the more applied side of it, and this first case is a byproduct of this 4D model that I constructed for Nimbus. So when I analyzed the different type of galenas, what I did is I used a technique which is determining in high resolution the difference in light isotopes. I'm going to describe a little bit the technique so that you understand like how much time and effort is constraining that. So the amount of galena that we need is very, very small. That's because, you know, galena is formed mainly by lead, and we need to measure very, very small amounts of that to get good results. So basically what we do is we just, with the little scalp, we will cut out a little piece of galena, and the amount of galena we need to measure it is 0.01 milligrams. Alternatively, what we've done successfully is we'll get a tin section and then put like 1 drop of HBr, so very, very small amount of HBr, and leave it for 1 minute. And that is enough time for the lead in the galena to be dissolved into this acid and then be put into solution. Once we do that, we'll just dissolve it further in a weaker acid, and then we'll measure the lead composition from that solution. So we measured the lead isotopes at UWA using the multi-collector, and the chemical differences that I was able to observe are due to the fact that we use this high resolution technique. So what we do is we spike it with a 207, 204 lead, and then we use a routine that was established in Southampton called the Southampton double spike method. And in the graph here to the right, you can see that compared to previous data that used the more traditional sample bracketing, we get like 10 times more precise determinations. So based on that, I was able to remark the differences in chemistry between the two galenas. So first of all the galenas which are related to the ore, they cluster here with a very homogeneous composition. So these are the galenas here circled in yellow. And then this other circle here is in the wrong position, but that's not a mistake. I was just trying to test the audience. That should actually be here on the ore cluster. And then the late galenas, they're spread around this mixing line, which represents mixing from 3 different sources. The original ore cluster, an older component, which is basically present in the sediments, and most importantly, the young lead which evolved through time. Now, this is important because when we plot those 3 points of late galenas in a map, what we observe is quite interesting, is that the further you get from the actual position of the ore bodies, the more towards the younger signature you get. And this is showing us that these galenas are the result of, you know, the remobilization of the lead that was there in the ore, as well as the introduction of a new component, and that could be possibly developed into a vector towards ore, where the closer you get to a signature of ore cluster, then the closer you get to the ore. And I mean, because you have such a you know, you don't really need that much sample, so it's actually something quite easy to test out for these different deposits. And then moving to the second portion of what I want to show today, I also did some measurements of trace elements using laser ablation ICP-MS of sedimentary pyrites. Now, in this case, I am really concentrating on this little unit here, which overlays the mineralized rocks of the deposit. And I was interested in understanding what's the relationship between the sedimentary sequence to the remainder of the deposit, and could I understand the conditions, the paleo conditions of this environment. So now I'm looking at the pyrites from number 7, which are distal siltstone hosted pyrites. So first of all, when you analyze the polymetallic ore sulfides, the ore sulfides, including the polymetallic, you have these different signatures of antimony over silver ratios. So we managed to identify that there is, an empiric observation of difference in ratios of antimony over silver, which seems to characterize these 3 different phases related to ore, and that's basically what I'm going to use in my exploration. So before I can apply that to my sequence, first I had to understand what's the relationship of the sediment with the rest of the deposit. And to do that, I dated the black shale containing nodular pyrites with rhenium osmium, and I obtained the age of 2680 million years plus or minus 34. And when I plot that against our other geochronometers for the Nimbus deposit, I'll see that it is actually cogenetic or coeval to the volcanic sequence. So this sediment was being deposited at the same time that the volcanism was active and the mineralization was going on. So knowing that, I collected samples from different positions in the drill core, and then I did a little transect to measure the trace elements in the ICP-MS, and I basically used only the cores because I think that represents better the seawater conditions at the time. And using the little typical zones that we have of chemical composition, I compare the samples from different levels, and what I observed is the existence of an enriched horizon with increase in trace element content, which corresponds also to signatures that approach the polymetallic zone. And the idea here basically is that while this system was active, metals were being leached to into the seawater, and that increase in metal content was recorded by the sedimentary sequence. So the idea is, if you have a distal sedimentary sequence which contains sedimentary pyrites, by looking at the trace element content of different positions, you might be able to track activities which are happening close by or a little bit distal to that. So, you know, even if you hit, even if you don't hit mineralization in your drill core, that doesn't mean that you just wasted all this money. Just, you know, take a little sample, bring it to Curtin. You can do basically 300 to 400 points in a single night, and maybe you'll be able to get something interesting that can help you track activity in a distal fashion. And just interestingly, if you compare our results to a typical half-core assay, you see that the variation that we get in silver by analyzing the pyrite is not recorded by the half-core assay, and that's because everything is just diluted in whole rock. I hope that you had some good ideas from this. Thank you.